Hello everyone, this is the second lecture on quantum mechanics. Today we are going to talk about normalization. Last time we've talked about the Schrödinger equation and wave function should be normalized by Born's statistical interpretation. And here is the normalization condition. When we integrate the probability density of particle in whole space, it should be 1. And intuitively, this means that this area must be 1. As Schrödinger equation, did you remember this formula? I haba partial t psi equals to h psi. If psi is the solution, so is the a psi. Here a is from the complex. Since if we plug this in, we get the exactly same form of this Schrödinger equation. So verified. Also, if psi1 and psi2 are the solution, so is a linear combination, a psi1 plus b psi2. You can check very easily. Just plug in. So the whole structure of solving the equation and normalizing is right here. Solve the Schrödinger equation and get psi. If psi is square integrable, we just normalize it. And we reject non-normalizable solution, such as when we integrate this norm squared, we get infinite values. It is meaningless, so we reject this solution. And also note that Schrödinger equation has solutions such that the normalization is preserved. So you can ask me that when we just normalize some psi, but how can it be guaranteed that as time t goes on, it still stay? Which means t equals 1, its normalization condition hold, but t equal 2, is it? So let's check. We can just differentiate this normalization term from minus infinity to plus infinity, and we differentiate d by t. And then the result is 0 if the normalization condition is preserved. You know that d dt something quantity is 0, that means the quantity is preserved at time. So just calculate and calculate. Blah, 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 like this. Very simple. Here, step, I used this. And then next step, I recall the Schrödinger equation. Here, I haba partial t psi equals h psi and minus I haba partial t psi conjugated equals to h psi conjugated. You just plug in like this, and note that h was this. H was the Hamiltonian operator, so the boring calculation is going on, and then we get finally this step. Note that here is an integral by parts. You just do this integral by parts like this, and here second term and last term canceling out, and we got this. And the infinite, at the infinite side, the psi must be 0, Because if not, the normalization doesn't make sense. No, the psi squared. So psi, if psi doesn't go to 0, for example, goes to 1, oh, integral must be blowing up. So the psi must go to the 0 as x goes to infinity. So we got 0. That's it. So as a conclusion, if we differentiate this normalization integral by t, we get 0, which means normalization is preserved. Verified, QED. Okay, next we're gonna solve two problems about normalization. The key point is that you have to do the integral. So let's do this. At time t equals 0, a particle is represented by the wave function psi x0, a x divided by a when x is between 0 and a b minus x divided by b minus a when x is between a and b, and otherwise 0. Here a and ab is positive real number. So first we have to normalize that. Just use the normalization condition like this. And then the remaining part is just a mathematical calculation. So simple, simple, simple. Then we have to distinguish the constant and variable terms like this, and just integrate that. And we get finally the value of a like this, square root 3 over b. Next, we have to sketch the graph of psi as a function of x. So as you can see, the algebraic representation of this psi here is positive slope line, and here is negative slope line like this. And at the boundary, if you plug this a to both sides, you get the exact same value a, right? So this is the continuous function. So intuitively, positive slope line and continuous and negative slope line like this. So the result is very simple like this. So C, where is the particle most likely to be found at t equals 0? No doubt, it's A, near A, right? If you integrate this graph like this, you get the highest value of integration near the A. So the answer is neighborhood of x equals A. D, what is the probability of finding the particle to the left of A? Check the limiting case b equals A and b equals 2A. Very simple. The left of A meaning minus a to a integral. So you can just integrate this by the simplest procedure. Integrate those terms and get the result as a over b. So if we check the limiting case, if b equals a, the result is 1, and b equals 2a, the result is 1 over 2. Lastly, what is the expectation value of x? So only the definition of expectation value matters. So bracket x is just the whole space integral of x, norm squared of psi x, and this exactly same with this integral 0 to a to b, and function. You can recall the function from this original definition of psi, like this. And then got this. And boring calculation is going on, going on, going on, going on. And here you see this change of variable, common integration trick, and you got this outcomes. Just calculation. Okay. Next problem, 1.5. Consider the wave function psi xt is a exponential minus lambda absolute value of x exponential minus I omega t. So here you can see the I. So this psi is actually in complex plane. So when we take the norm of this psi, we have to do the process to find the norm value, like psi conjugate and product it with the psi, like this. So here, when we normalize psi like this, integral whole space, norm squared means exactly we have to do this product psi conjugate psi. The result here, two exponential terms canceling out, and we got this, and we do this integral by parts, not the trig integration by part, just part by part. So in R plus domain, the absolute value popped out just x. Also, in negative domain, the absolute value is popped out with minus. So minus is canceling out to be a plus. So we just calculate this integral to get the final answer, a equals to square root of lambda. B, determine the expectation values of x and x squared. Just use definition. Expectation value of x is just this integral, x norm squared of psi xt, and you just use the definition of psi and calculate those terms. We also used this change of variable, and you got this 0. But here is some fun things. You can just expect the outcomes before this whole dizzy calculation. Why? What was this? Psi norm squared. It was this. A squared exponential minus 2 lambda. Absolute value of x. But here, you know that this is even function. And when we multiply x is odd function, with even function, the whole function is odd. So when you integrate this in whole space, you can just get this 0 value. Intuitive. Similarly, you have to check the expectation value of x squared. Simple, but here is some tricky integral here. Have you seen that? X squared exponential minus lambda x. So, trick is here. How can you find this? So consider first integral 0 to plus infinity exponential minus lambda x dx. We can just integrate this explicitly simply, and then divide both sides by lambda. I mean, it's differentiate both sides by lambda. And we get this, and we one more time we get x squared is popped out. So we get this. So you can just plug in, and then we solved it. We found the expectation value of x squared. Next, find the standard deviation of x, sketch the graph of psi norm squared as a function of x, and mark the points from bracket x plus sigma and bracket x minus sigma. What is the probability that the particle would be found outside this range? We can find this sigma by the simple formula square root of bracket x squared minus bracket x squared, and just plug in. This is what we just found, and this is also what we just found as 0, and the resulting sigma is 2 over lambda. And the sketching graph is simple because it is even function, and the both left side and right side tails have to go to the 0 to be normalized. So you can intuitively expect the exact structure of the geometry of this graph, like this. And next question was that you find mark the points here, but here expectation value of x was 0, so you have to just mark plus sigma and minus sigma point, and we find the sigma as 2 over lambda. Just point it. And then what is the probability that the particle be found outside this range? You have to just integrate this part. Since this function is even function, the strategy is just find this area and then multiply it by 2. So we have to just find this area by this simple integration, blah blah blah, and we get this, and then multiply it by 2, we get this final outcome. That's it. Today was some kind of heavy calculation or not, but it was still fun. So if you enjoyed it, please subscribe and like, and most of all, enjoy the physics. Bye bye.